Hello everyone, in this video we are going to solve all the evaluate yourself questions from unit 2 quantum mechanical model of atom. So let's do this one by one. Calculate the de Broglie wavelength of an electron that has been accelerated from rest through a potential difference of 1 kilo electron volt. We know that de Broglie wavelength lambda is equal to h divided by p. H is the Planck constant and p is the momentum, and therefore this is equal to h divided by mv. We know the value of Planck constant, that is equal to 6.626 times 10 to the power minus 34 joule second, and the mass of the electron is 9.1 times 10 to the power minus 31 kg. What is the velocity of electron here? That is not given directly in this question. It is mentioned in an indirect manner which we need to figure it out. What is mentioned in the question? An electron that has been accelerated from rest through a potential difference of 1 kilo electron volt. This means that when we don't apply any potential difference, the electron is at rest, and that means its velocity is 0, because we have an electron that is at rest. This means that velocity is 0. That means the kinetic energy of the electron is equal to 0. Now, after we apply the potential difference, the electron moves. So, when we apply the potential difference to the electron, now the electron moves, and that means it got some velocity that we need to find out, and this means that now it got kinetic energy, because any moving object with mass should have kinetic energy, and therefore that is equal to half mv square. Therefore, we can equate the energy due to accelerating potential with the kinetic energy of the electron. Therefore, half mv square is equal to ev, because that kinetic energy whatever the electron gets is due to the potential difference that we are applying. Therefore, we can equate that ev is equal to half mv square. Therefore, mv square is equal to 2 ev, and if you multiply on both sides with m, we can write that mv whole square is equal to 2m ev. Therefore, mv is equal to square root of 2m ev, and this we can substitute here so that we can find out the lambda value. So, let us find out this value of square root of 2m ev. Therefore, square root of 2m ev is equal to 2 times 9.1 times 10 to the power minus 31 kg times, here ev is mentioned as 1 kilo electron volt. This means this is equal to 1 times 10 to the power 3 times 1.6 times 10 to the power minus 19 joules, because the charge of an electron is equal to 1.6 times 10 to the power minus 19 coulombs, which multiplied by 1 volt gives this value. Therefore, 1 times 10 to the power 3 times 1.6 times 10 to the power minus 19 joules to the whole power 1 by 2. Let us work on the unit before we figure out what is the square root of 2m ev. In the numerator we have Planck constant, in the denominator we have square root of 2m ev. So, here we have joule second, and here we have joules kg to the whole power 1 by 2, and therefore this will become joules to the power 1 by 2 kg to the power minus 1 by 2 second. We know that 1 joule is equal to 1 kilogram meter square per second square. So, if we substitute that here, then what will happen? This will be kilogram to the power 1 by 2, meter square to the power 1 by 2 will become meter, per second square to the power 1 by 2 will become per second, and then this time we have kilogram to the power minus 1 by 2 and then second. So, this will cancel out, this will also cancel out, and what would remain is only meter. That's what is going to be our unit. So now let us work on square root of 2 MeV. So here we have 10 to the power minus 31, here 10 to the power 3. So that will become 10 to the power minus 28, and then from 10 to the power minus 28, here we have 10 to the power minus 19. So that will be, if we add up, 10 to the power minus 47, and therefore this is equal to, let us multiply 1.6 with 2. So 3.2 times 9.1 times 10 to the power minus 47 to the whole power 1 by 2. We can't take square root of an odd number, and therefore let us multiply and divide by 10. So in that case, we can write that square root of 2 MeV is equal to 32 times 9.1 times 10 to the power minus 48 to the whole power 1 by 2. 32 times 9.1 is 291.2, and this will be 10 to the power minus 48 to the whole power 1 by 2. So that will become 10 to the power minus 24. We have 1 by 2 here. 17 times 17 is 289, and therefore this will be approximately, we can write it as 17.1 times 10 to the power minus 24. So that's the value we have for square root of 2 MeV. Therefore lambda is equal to 6.6 times 10 to the power minus 34 divided by 17.1 times 10 to the power minus 24 meter. So this we can write it as 66 times 10 to the power minus 35 divided by 17.1 times 10 to the power minus 24. Therefore 66 divided by 17. So that will be 3 times will be 51, remaining 15. So rise it to the decimal, and then 8 times will be 136. So approximately 3.8, and therefore lambda is equal to 3.8 times 10 to the power minus 11 meter. Let's do question number 2. Calculate the uncertainty in the position of an electron if the uncertainty in its velocity is 5.7 times 10 to the power 5 meter per second. Here delta V is given as 5.7 times 10 to the power 5 meter per second. We know from Heisenberg uncertainty principle that accurately measuring both the position as well as momentum for a microscopic particle is not possible simultaneously. By the time you try to measure the position accurately, the velocity will be changing. Let us say this is the nucleus, this is the electron. So if you try to measure the position accurately, the velocity will be changing. If the velocity is changing, momentum will be changing, because P is m times v. So if you try to measure the momentum accurately, then the position will be changing. So therefore simultaneously measuring both the position and momentum accurately is not possible as per the uncertainty principle, and therefore delta P we can write it as m times delta v. Therefore we can say that delta x times m times delta v is greater than or equal to h divided by 4 pi. Here they have mentioned about an electron, and we know that mass of an electron is 9.1 times 10 to the power minus 31 kg. Planck constant value h is equal to 6.626 times 10 to the power minus 34 joule second, and we know that 1 joule is equal to 1 kilogram meter square per second square, and therefore we are going to calculate the delta x here. Therefore delta x is equal to 6.626 times 10 to the power minus 34 kilogram meter square per second square divided by 4 times pi value is 3.14 times 9.1 times 10 to the power minus 31 kilogram times 5.7 times 10 to the power 5 meter per second. So, we have a second here. Therefore, this will cancel, kilogram will cancel, meter square. So, what will remain is only meter. So, let us approximately take these values. So, this is like 1 times, this is 2 times, and then 2 times 2 is 4, therefore, this is 2, and then 9.1 we will take it as 9, and 5.7 we will take it as 6. Therefore, 9 times 6 is 54, 54 times 2 is 108. Therefore, 1 divided by 108 times, we have 10 to the power minus 34 here, 10 to the power minus 31 in the denominator. So, when this goes up, this will become positive. So, that will be 10 to the power minus 3 we will have. But we have 10 to the power 5 here. This will become negative when this goes up. So, 10 to the power minus 3, 10 to the power minus 5. So, eventually what we will get here is 10 to the power minus 8 meter. Now, if you take this 108 as approximately 100, then you can write it as 1 times 10 to the power minus 2 times 10 to the power minus 8. Therefore, this will be equal to 1 times 10 to the power minus 10 meter. So, that is the uncertainty in the position of the electron. Let us move to question number 3. How many orbitals are possible in the fourth energy level? N value is given as 4. The principal quantum number is given as 4. This means that we are in the N cell, because K, L, M, N. So, when N value is 1 here, 2 here, 3 here, 4 here. So, we are in the N cell. So, in the N cell, how many orbitals are there? So, this means that what would happen to the azimuthal quantum number? L runs from 0 to until N minus 1. So, this means what will happen to the L values? L will be 0, 1, 2 and 3, and this means that S orbital, L equal to 0 means S orbital, L equal to 1 means P orbital, and L equal to 2 means D orbital, L equal to 3 means F orbital. And what will happen to the magnetic quantum number? So, we found that azimuthal quantum number, but what will happen to the magnetic quantum number? Magnetic quantum number is minus L to plus L through 0. So, this means, so the magnetic quantum number in this case will be simply 0, but here it will be minus 1, 0, plus 1, here minus 2, minus 1, 0, plus 1, plus 2, and here it will be minus 3, minus 2, minus 1, 0, plus 1, plus 2 and plus 3. So, here you will have only one orbital, here you will have 3 orbitals, here you are having 5 orbitals, 1, 2, 3, 4, 5, and here you will have 7 orbitals, 1, 2, 3, 4, 5, 6, 7. So, 1, 3, 5 and 7, and that means the total is 16 orbitals. So, we will be having 16 orbitals for the fourth energy level. That is the correct answer. We can directly find the number of orbitals through N square. However, it is better to understand through principal quantum number what will happen to the azimuthal quantum number. When azimuthal quantum number is having different values, what will happen to the magnetic quantum number. So, it is better to have a complete picture instead of directly writing the answer. Let us move to question number 4. Calculate the total number of angular nodes and radial nodes present in 3D and 4 of orbitals. First of all, what is a node? The region where the probability of finding the electron is 0. For example, let us say we have a 2px orbital. Electron could be anywhere here or here, but in between at this particular region the probability of finding the electron is 0. So that's what we define it as a nodal plane. So for p orbital, let's say for 2px orbital in this case, the angular node will be equal to 1, because for p orbital the value of L, the azimuthal quantum number, is equal to 1. So let us calculate the total number of angular nodes and radial nodes for 3D and 4F. The total number of nodes is always equal to n minus 1, where n is the principal quantum number. So we have two different orbitals. Total nodes is equal to n minus 1. For 3D, what is the value of n? N is equal to 3. That means what should be the value of total nodes? Total nodes should be 2. And what is the value of L for d orbital? The azimuthal quantum number value is equal to 2. The total number of angular nodes is simply equal to the value of azimuthal quantum number, and therefore the number of angular nodes for 3D is equal to 2. How about radial nodes? Radial nodes in this case is equal to 0, because we already got the total value here. The number of radial nodes is always equal to n minus L minus 1. Therefore in this case 3 minus 2 minus 1, and that's how we got 0 here. How about 4f orbital? In the case of 4f, the value of n is equal to 4, and for f orbital the value of L is equal to 3, and therefore what would be the total number of nodes? 4 minus 1, 3, and the angular nodes will be equal to 3, therefore the radial nodes will be equal to 0. This is simply 4 minus 3 minus 1. Let's do question number 5. Energy of an electron in hydrogen atom in the ground state is minus 13.6 eV. In that case, what is the energy of the electron in the second excited state? The E1 value is given as minus 13.6 eV for the ground state. That means n value is equal to 1. The general expression is for the nth stationary state, En is equal to minus 13.6 times Z square divided by n square. Z is the value of the atomic number. For hydrogen atom, it is 1. N is the value of the stationary state. Here they are asking the second excited state. This means ground state, first excited state, second excited state, which means n value is equal to 3, not 2. Just because it is mentioned as second excited state, it doesn't mean that the n value is 2, it is 3. This is the second excited state. This is the first excited state. This is the ground state. Therefore, E3 is equal to minus 13.6 times 1 square divided by 3 square EV. Therefore, this is equal to minus 13.6 divided by 9. So, if we keep it as 136, then 15 times 9 is 135, remaining 1 we can't divide. So, put a 0. So, 1 times 9 is 9. So, this will be keep going, but we have to multiply with the 10 to the power minus 1. So, therefore, minus 1.51 eV. That's the correct answer. That's the energy of the electron in the second excited state. Let's move to question number 6. How many unpaired electrons are present in the ground state of Fe3 plus, Mn2 plus and argon? Atomic numbers are given in parenthesis. In a neutral element, the number of protons must be equal to the number of electrons. When they give atomic number, what it means? It means it contains that many number of protons. Here, everything is not neutral, only argon is neutral. Fe3 plus, Mn2 plus, they are charged species. Therefore, in Fe3 plus, how many electrons will be there? We will have 23 3 electrons here. Even though the number of protons will be 26, when it comes to number of electrons, it will be only 23. Let us write the electronic configuration of neutral ion first, and from there we will remove 3 electrons. To write the electronic configuration, we need to follow the aufbau principle or the build-up principle, and therefore it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, because the neutral ion has 26 electrons. Here we have 26 electrons, 26 protons. So, for 26 electrons we wrote the electronic configuration by following the aufbau principle. Now, the question is, should we remove all the 3 electrons from the 3d orbital? No. When we remove electron, we should remove electrons from those orbitals that has a higher value of principal quantum number. Here the principal quantum number is equal to 4, but for 3d the principal quantum number is 3, even though 4s2 get filled first and 3d6 filled later. When we remove electrons, we should remove electrons from those orbitals that has a higher value of principal quantum number. Remember, this 1s2 electrons, they are in K shell, n equal to 1. This 2s2 and 2p6, n equal to 2, they are in L shell. This 3s2, 3p6 as well as 3d6, these 14 electrons for which n value principal quantum number is equal to 3 and they are in M shell. These 4s2 electron, that is in N shell, n value equal to 4. Therefore, these electrons must be removed first before we remove any electron from 3d. So, in this case it is Fe3 plus. Therefore, we need to remove 3 electrons, 2 from 4s2, 1 from 3d6. Therefore, the electronic configuration now will be, let us follow a shorthand notation, that is simply write it as argon that has 18 electrons and then 3d5. This 3d5 will have 5 unpaired electrons, and therefore the number of unpaired electrons in Fe3 plus in the ground electronic state is 5. Now, let us go to Mn2 plus. Before we write the electronic configuration of Mn2 plus, let us first write the electronic configuration of neutral manganese, that is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5, because the neutral manganese element contains 25 electrons. Now, when it becomes manganese 2 plus, it will have 23 electrons. Therefore, once again the 4s2 electrons should be removed. That means for Mn2 plus the electronic configuration will be simply argon and 3d5. Once again we have 5 unpaired electrons. The number of unpaired electrons for Mn2 plus is also 5. Now, the next is argon. For argon, the electronic configuration is simply 1s2, 2s2, 2p6, 3s2, 3p6. All electrons are paired up here, and therefore the number of unpaired electrons in the case of argon will be 0, no unpaired electrons, because everything is paired up here. It contains 18 electrons. In total it contains 18 electrons. However, when it comes to number of unpaired electrons, it is 0. Let us do question number 7. Explain the meaning of the symbol 4f2. Write all the 4 quantum numbers for these electrons. The 4 in 4f2 means that the principal quantum number is equal to 4. That means we are in the 4th energy level or 4th orbit. Let us consider this is the nucleus of the element. This is orbit 1, this is orbit 2, this is orbit 3 and this is orbit 4. N equal to 1, n equal to 2, n equal to 3, n equal to 4. This is the K cell, L cell, M cell, N cell. We are in the N cell. These two electrons are in the N shell. The letter F describes the subshell, F orbital. That means the azimuthal quantum number. The L value must be equal to 3 because L runs from 0 to n minus 1. When L is equal to 0, it means s orbital, L equal to 1 means p orbital, L equal to 2 means d orbital, L equal to 3 means f orbital. Because the n value is equal to 4, L can have values 0, 1, 2 as well as 3. So, it is mentioned as f and therefore, the L value is definitely 3. Now, what will happen to the magnetic quantum number? Magnetic quantum number runs from minus L to plus L through 0. This means it can have the following possible values, could be minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3, 1, 2, 3, 4, 5, 6 and 7. However, we only have 2 electrons. So, 1 and 2. That means that for one electron it is going to be minus 3 and for the other electron it is going to be minus 2. How about spin quantum number? Both the electrons will have plus half, that means they are up spin or rotating clockwise. We have 2 electrons, both are up spin. Why we are not pairing them up in one orbital? Because we need to follow the Hund's rule. When multiple orbitals of the same energy are available, electrons will occupy different orbitals singly and with the same spin before any are occupied doubly. Therefore, we should not consider pairing up here, that is not allowed as per Hund's rule. To summarize, let me write all the 4 quantum number for these 2 electrons. So, n value is 4, L value is 3 and then ML is minus 3 for one electron and then the spin quantum number is plus half. For the second electron 2, n value is 4, L value is 3 and then the magnetic quantum number value is minus 2 and the spin quantum number value is plus half. So, these are the 4 quantum numbers for the 2 electrons, 4f2. It is the magnetic quantum number that differentiates these 2 electrons. Let us do question number 8. Which ion has the stable electronic configuration, Ni2 plus or Fe3 plus? Let us first write down the electronic configuration of both of them and then we will decide which one is more stable. To write the electronic configuration, we need to follow the aufbauprinciple or the build-up principle. The easiest way to do is write the orbitals like this: 1s, 2s, 2p, 3s, 3p, 3d and then 4s, 4p, 4d, 4f and then put a slanting line like this. Start from here, end here, start here, end here. So, that it is easy to remember. The atomic number of nickel is 28. So, let us first write down the electronic configuration of nickel. In a neutral element, the number of protons must be equal to the number of electrons. This means nickel has 28 protons and 28 electrons. So, let us write the electronic configuration: 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2, and then after 4s2 we are going to 3d. In 3d we should have only 8 electrons, because until here it counts to 20, isn't it? 20 electrons and then plus 8. So, therefore, 28 electrons. Now, if we say nickel 2 plus, this means we removed 2 electrons. Now, the number of protons will be the same, but the number of electrons will be 26. Electrons must be removed from the outer orbit. Here the n value is 4. Therefore, electrons must be removed from 4s2 first. Therefore, the electronic configuration now is, we can simply put it this way: argon that has 18 electrons until here, that is argon, atomic number of argon is 18, and then the 2 electrons from 4s2 they are removed now. Therefore, 3d 8, and the 3d electrons, the 8 electrons can be filled this way: 1, 2, 3, 4, 5, and then 6, 7, 8. Now, let us write the electronic configuration of Fe3 plus. For Fe, let us first write the electronic configuration. Atomic number is 26, and therefore, argon that has 18 electrons, and then 4s2 20, and then 3d 6. Now, if we say Fe3 plus, this means now the number of protons will be still 26, but the number of electrons will be only 23. Therefore, for Fe3 plus it will be still argon 18 electrons. Both the electrons from 4s2 will be removed now, and 1 electron from 3d6 will be removed. Therefore, this will become 3d5. We have 5 electrons in the 3d orbitals here for Fe3 plus. This electronic configuration is more stable than nickel 2 plus, because this is half filled. It is symmetric and the exchange energy is more. So, in general, half filled or completely filled, that means D10. Half filled or completely filled d orbitals are more stable compared to partially filled d orbitals. What we have for nickel 2 plus is 3d8, isn't it, which is partially filled. So, we have 8 electrons there: 1, 2, 3, 4, 5, 6, 7, 8. So, this is partially filled and not symmetric, whereas this one is half filled and completely symmetric. Therefore, Fe3 plus is more stable than nickel 2 plus for 2 reasons. One is symmetry and the second is exchange energy. What we mean by exchange energy is, when we have 2 or more electrons in the d orbital with the same spin, there is a possibility of exchanging their positions. For example, this electron, let us say this is the first electron, instead of going here, it can go here or here or here or here. That means 4 different exchanges are possible. Likewise, when the second electron comes in, 3 different exchanges are possible. Then when the third electron comes in, 2 different exchanges are possible. Then when the fourth electron comes in, 1 exchange is possible. So, therefore, overall 10 different exchanges are possible when we have half filled d electrons, whereas here only 1 exchange is possible. Instead of going here, it can go here, because this is already paired up. So, therefore, only 1 exchange is possible here, but for Fe3 plus 10 different exchanges are possible. Therefore, Fe3 plus is more stable than nickel 2 plus.